As you're probably aware, we measure things in sort of a standard unit. Now, there's actually standard international units, or what we refer to as SI units, and then there's maybe what you consider to be sort of a standard of measure. The first that we're going to talk about is that of volume. So volume is in liters, and that's a big L abbreviation. Now, cool thing is that SI units for this is meters cubed, but usually we use liters as a measurement there. Length is that of meter. Now you're saying, well, why is that SI unit in meter cubed? Well, keep in mind, if we have length times width times depth, what we actually make is a cube, and that can carry volume. I can't draw, sorry about that, y'all. Okay, next we have mass, and mass is in grams. So in the SI unit, though, this is in kilograms, and in a future video we'll talk about what that K in front of grams means, but essentially means there's 1,000 grams in 1 kilogram. Next we have temperature. This is not in Fahrenheit. This is in degrees Celsius. So degrees Celsius is what we usually measure things in. We want to convert that into Kelvin, which is a big K, not a little k as you have in kilogram. And that big K, Kelvin, there's a little equation that goes along with that we'll talk about later. Time, finally, is in seconds, not minutes. And that is abbreviated as S, not SEC. So something to be aware of there. Now, when we go to measure things in the laboratory, we have to make sure that we're taking accurate measurements. There are certain instruments that give us that accurate measurement, and we can only write down what it gives us. Like a balance might give you 3 tens digits. And so what we do is we just write all of that information down. But when you can see something that you're measuring, you have to estimate between the last two hash marks that are there. Let me show you what I'm talking about. So we want to take precise measurements. We want to take accurate measurements. I'm not going to go into what the difference of those two things are, but basically we want to estimate the last number where possible. Okay, let's say that we are measuring with the ruler that we have below. So this has centimeter marks, right? And if I'm measuring this red line that's right here, I have to sort of estimate what value of centimeter we have here. So to the next digit. That means that if I've got something that's coming about right here, I would probably estimate that to be 2.2 or 2.3 centimeters. Know that I can put the next tens digit there, so 0.2 or 0.3. That is not in my measuring device, but that is something that we estimate. So our data is going to depend on our measurement tool. So we can only get us to this level of precision with our data. You can't say that that's 2.356 centimeters. That would be incorrect to even attempt to do that. However, if we have a more precise tool, let's say that we have lots of hash marks in between our centimeters, like we see here. Well, I'm going to take a line, and let's see, I'm going to put it right down here. And so I can now estimate between those two hash marks and get another tens digit out of our measurement. So here we can get to the 0.01 centimeter, where we can only get to the 0.1 centimeter before. So I'm going to estimate that as being about 2.45 centimeters. So we have more precise data because our tool is more precise. Now you may already realize this, but in case we don't, when you measure liquids, you use a graduated cylinder. And what you want to use is you want to use the bottom of the meniscus. And the meniscus is this line that's created. Not all liquids have that meniscus that's very prominent, but certainly with water you do. So you read the bottom of that meniscus because that's how we measure things. And in this case, I'm going to again estimate where that is, and it would give us a reading of 1.4 milliliters. So that means the precision of your measurements depends on your tool. It depends on what device you're using. And therefore, that means that measurements aren't necessarily the same and data is not the same. We cannot have more precise calculations than we have in our data to begin with. This little dot, 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 if you remember in math, means therefore we must look at our data to know what is reliable or what digits are considered to be significant. So there's a method to that madness. We can determine and count the numbers or the digits that are significant in our data. And it doesn't get difficult until we really deal with zeros. Because the first rule is all non-zero numbers are significant. Okay, I don't say all often, so that means that they're all significant. So here I've got 6 digits. They're all significant. So our data is significant for 6 figures. But it's harder to see what to do with zeros. So let's look at those. Zeros that are between 2 non-zero numbers are significant. So in other words, this one right here, it's embedded between a 2 and a 4. It counts. It is a significant figure. We have 4 significant figures there. The next thing that we have to realize is that zeros after non-zero numbers are assumed to be not significant. There's a big thing here though. Unless a decimal point is present. So if a decimal point is present, all zeros after the non-zero number is significant. Okay, so let's count that on this very first one. This first one we have 1, 2, 3, and then we don't have a decimal point, so there's only 3 significant figures. But the moment this decimal point comes in here, it's like it declares that is significant, and I must count that 0. So now we have 4 significant figures. And if these zeros keep going, even after that declaration's way back here, it still counts. That means that all of these numbers would be significant. Okay. Now, zeros that precede non-zero numbers, sorry about that. Zeros that precede non-zero numbers are placeholders. They're not significant. So, like this guy, those zeros, they don't do anything except for hold the place of that 329. So here we've got 329. Those 3 are significant. Now, it's different when you have a 0 that's again embedded between 2 different numbers. And in the same regard, if we had 0.0300, these would all be significant because they follow a 3 and a declaration of a decimal point. But these 2 would not. Okay? Before I go to the next page that gets more difficult, please know that there's another video showing examples of these. If you want to pause this here and go practice some more of those counting of significant figures, please feel free to do that. Okay. So now we're going to talk about how to use significant figures when it comes to calculating things, because that's really important. Okay, so let's establish some rules for that. First, we're going to start with addition and subtraction. This is honestly the more tricky version to see, but we're going to round our final value, so we add things together and then do this rounding bit, to the number of decimal places that is the one in your data set with the least number of decimal places that are represented. So if I add all of the things that are listed here together, right, we get a very detailed number. But this one right here only goes to 21.2. So we only go to the 0.1 type of digit. And so our final reported value can't have all this detail in it. We need to round the 0.6959 to simply 0.7. Okay? So when it comes to addition and subtraction, that's one set of rules. Honestly, I think we use multiplication and division more in chemistry for the most part. But in multiplication and division, what we do is we look at our data set. And we're not talking about exact numbers, and we'll talk about that more in a minute. But what we do here is we round to the number of significant figures that is equal to the number in your data set with the least number of significant figures. So in this case, we have 21.0. That's 3 significant figures. Here we have 32.349. That's 5 significant figures. 3 is less. And we're dividing by something with only 2 significant figures. So since the one on the bottom has the lowest number of significant figures, that's what we're going to report our final data in. Go ahead and put this into your calculator and get the number that it spits out. You don't have to write everything, especially if you don't have to use it. But our final reported value should be in 2 significant figures. So we can say that as 130, or if you're worried about zeros, if you put this in scientific notation, that should just be the only thing that's before the times 10 to the whatever it may be. Okay? So there's specific rules as to rounding up and rounding down. We're not going to do all that. If it's 5 or higher, round it up. If it's 4 or lower, round it down. Okay? Now, I mentioned exact numbers. Exact numbers do not count on these values. So, for example, if I count that there's 53 humans in a particular room, that's an exact number. There's not like 53.2. And so when we're considering exact numbers, they do not play into account when it comes to significant figures. Another example is an inequality that has the right number in it. So for example, there are 12 in a dozen. This 12 does not count towards significant figures. That's not something that we worry about. So if we have 392 dozen letters and we're trying to tell how many letters that is, then that gives us 4,704 letters. So our final answer should be in 3 significant figures. Why? Because this is 3 significant figures. And you might say, ooh, how do I do that? Because if you say it's 4,700, then that looks like it's 2 significant figures. Well, that's where we come into play with scientific notation. That's about the only way that I know of to really show that there's 3 significant figures there. So that's something to keep in mind. We're going to practice this. I'm going to have another video just based on practicing significant figures and their calculations. So please make sure that you attempt that as well. Thank you.